Good, so we jump on a completely different topic with Dr. Yair Linn. He's coming from Canada. He's currently an FPGA engineer in Triumph. He has over 30 years of experience as an FPGA and ASIC designer in both industry and academia. And in his talk today, he will walk us through some key limitations of SystemVerilog and the elegant solutions he has developed to address them.
Thank you. Thank you so much. Yes, so thank you for coming to this talk. Yeah, so this is SystemVerilog hacks, circumventing the limitations of SystemVerilog. It's a very practical talk. You know, can I just have a show of hands who uses SystemVerilog at all? Okay, good. I was afraid that it would be too niche because VHDL has got more presence in Europe compared to North America, but I see many people use SystemVerilog. That's great. So this might be useful for you. So SystemVerilog has been used in FPGA and ASIC HDL design for more than 2 decades. It's a mature, very popular language. I'm sure most of you know that it was, Verilog itself was never really designed to be a synthesis language, so it's got some weirdness based on that. And also SystemVerilog, the way it was designed was, first it was done by a sort of a group, an unofficial group, not by the standards group, and then the standard, it got adopted by the IEEE standard group. So the standard really evolved very fast and without too much thought anywhere during this process. I think it's great, don't get me wrong. I think it's a really great language. But some things are really missing. In my opinion, or at least not clear. So it's a very powerful language for synthesis. But if, you know, it still causes HDL designers to expend significant work to circumvent some things that simple tweaks in the language standards could have solved. You know, so I will deal in this presentation with synthesizable Verilog. I mean, SystemVerilog. SystemVerilog for verification is a completely different subject, much bigger standard. So I'm talking about only synthesizable stuff. Everything I've shown here has been used in practice and I know works in practice. All the code that you see here is working production code. So it's not theoretical, it's all very practical. Okay, so let's get straight to it. So hack number 1, connect pins effortlessly and without errors down the hierarchy. So many times you have, you know, ports at the top, but the module that actually deals with those ports is somewhere down the hierarchy. It's not the top level mode. It's not, maybe it's not even the 2nd level. It could be 3rd or 4th level. And the, you know, the sort of conventional way to do this is, you know, you have a port list at the top. You have a port list in every module going down the hierarchy, and you just connect the ports, you know, one level of the hierarchy after another. It's fine. It works, but it's tedious. And it's error prone because you have to repeat all the port names everywhere. You have to connect it everywhere. Now, yeah, you have to make it in the, not just the connection, but also, of course, the definition of the modules, right? It's just annoying. So every change in the top level has to propagate to through to the hierarchy. So instead of doing that, let's use an interface to propagate signals down the hierarchy. Now, that in itself is not completely novel. That's what interfaces are for. But what we're going to do here is use a define to define both the interface and the top-level pins. And let's see how this is done. OK, so step 1, create a file with a define statement for the pins. This is an example for one of our modules. So this is from the neutrino experiments, I believe, one of them. So this is one file with the pin definitions. And this is the only place in the entire project where I define these signals. Nowhere else. Step 2 is I define an interface for those pins. And you can see here, so I call it the top level. I have this nice thing here, right? I need to point it there? Yeah? Well. OK, that doesn't work. I need to keep it pushed? OK, I'll try it. Let's try it. Oh, the top button? Top button. Okay, we got it. Okay, so you see here is where I instantiate that macro I just defined. So really what I'm doing, I'm making an interface with those pin definitions, those input and output pin definitions in there. I didn't repeat any definitions, they're right there. So this is this interface, and note that because I'm using this define, it automatically adapts if the pin definition change. Step 3, you can see the top level here also uses that same define, and the connection to the interface is done using the dot asterisk here, right? So this connects from here to the interface, and you can see here I've got the board-dependent top level, which also has this. So everything up to here is completely common to all the boards, essentially all the boards or all the designs we have. And the only thing that's changing now is the board-dependent top level. Even the syntax here is the same, but the contents of that board-dependent top level will be, as the name suggests, board-dependent. So you can see I only defined those pins one time. And now in the board-dependent top level, now I've got these top-level pins, which I can just push down the hierarchy as much as I want, you know, with that interface. I mean, here you can see, so I push it here, this top-level pins, I can push it here to this module here, the GP top level, general purpose top level, and this, I can push it down as much as I want. And here, at the end of the day, when I actually need to talk to those top-level pins, I can just reference them through the interface here. You can see here, I just reference whatever pin I want through the interface. So what happens? So pins are defined in only one place. I don't have to define them on all the headers of all the modules that go down the hierarchy. Defined in only one single place. So that, by definition, eliminates the possibility of mismatch in the connections, right? The top-level interface pins defs and top.sv are invariant, common to all projects, right? And also, even the board-dependent top-level pin declaration is invariant because just the internal contents of it are board-dependent. So the pins, therefore, are propagated effortlessly to the lower-level hierarchy. So that's one thing. So if I want to set up a new project, all I need to do, I don't need to do anything except define my pins once in that first top-level pin declaration macros file, and everything else stay the same. The board-dependent top-level contents obviously will change according to my project, and I can reference whatever pin I want down the hierarchy just by doing the top-level pins dot whatever the name of my pins are. Yeah. Just one tiny issue. I don't want to spend too much time over it, but just a quirk of, I guess, SystemVerilog is that if you have a stray space, which you can sometimes not see, that in the pin definition, you can see that stray space here. That kind of messes up the compiler. It gives you sort of errors. It sort of breaks the macro here, and then it thinks that the macro ended here and with a comma. If you get sort of weird errors, just enable see all symbols in your notepad or whatever and check for these stray spaces. That's the one pitfall that I wanted you guys to know about. Okay. I guess questions we'll do at the end, but let's move on to the second hack, which is extracting and using parameter values from interfaces. This one, to be honest, I did not think would work. I mean, I tried it. I mean, I hadn't seen it anywhere being documented, and I thought it was ridiculous to even try, but I tried it, and then it worked. So I'm like, OK, it works. Why not? Let's use it. So many synthesis tools, parameters and interfaces cannot be referenced like nets, or they cannot be extracted directly. I searched the web, and I saw that some simulation tools actually allow this. But I think that's sort of not part of the SystemVerilog standard. It's sort of like an extra thing that the simulators did. But I've never seen a synthesizer actually support this. So what this means, let me give you an example. Here I've got an interface. Okay, I've got an interface with a bunch of parameters. The number of channels, the number of data bits, number of bits per symbol, okay? And sometimes I need the interface. I need to look at an interface, or I want to look at an interface and figure out, how many channels does this interface have? How many data bits do these channels have, et cetera. So, for example, if I define an interface X, right, I can assign x.clock to something. Okay, that's perfectly legal. If I wanted to extract the number of bits, that's unsupported. I don't think it's even supported by the standard. Some simulation standards, some simulation tools might support it, but I've never seen a synthesizer support it. So here, it makes perfect sense that I could just, take a look at the number of bits here of the interface, but no. An even bigger sort of usage of this, really assigning it to a net, I can see scenarios where this would be useful, but the more useful scenario is taking it out and parameterizing a module with that parameter. So I want to take an interface and connect it to a module and parameterize that module based on the parameters of that interface. So if, for example, if my interface has 32 bits, 32 bits per data, then I want to do that. So the solution to do that is to define a function. And the function would be like the getter function. So instead of referencing directly, I call the function, right? So for example, get num bits per symbol or get num data bits. And that I can actually use. And what that means is, for example, here I've got two interfaces going in, and I can, I can get the number of bits and then get the number of channels here, and parameterize my internal structures based on those parameters. And note that what I did not have to do, I did not have to have parameters here. I didn't have to repeat the number of bits and the number of channels as parameters to this module. I can extract them directly from the interfaces that are at its input. And I'm sorry, I'm going a little fast because my time is running out, I'm being told. You can see here the connection here. I only connect the interfaces, and the entirety of the module automatically adapts to the various parameters of the interface by extracting them directly. And obviously, you can see here that this reduces the probability of errors, because now I don't have to propagate, independent of the interface, I don't have to propagate the parameters as well down the hierarchy. The hierarchy automatically adapts. Yeah. Hack number 3, parameterizable structs. So structs cannot be parameterized in SystemVerilog, and let me explain what I mean. You can do this. You can certainly do this. The bits per component, and if I have like a real and imaginary, I want a complex data structure here, I can do this. But I cannot do something like this. I cannot do something like this where I have a parameter of bits per component and then define, using the same structure, a 12-bit complex number, a 14-bit, a 16-bit. It makes perfect sense. This is illegal. This is not part of the SystemVerilog standard. This is what I wish were part of the SystemVerilog standard, but it's not. I would have to, what I need to do is something like this, which is ridiculous, right? I have to define bits per component different and define 4 different structures, right? Yeah, thank you. So you could define a package and parameterize the package, but it really does not. You could try to do this. You could try to do this and have a per package complex package. But the problem is you get name conflicts, because the complex data structs will now, when you import that, now you'll have the 4 different definitions of the same structure, each with a different number of bits, which causes conflicts. It will not compile. So you can define different packages with that doesn't help. That's not simpler. That's just more complicated. The solution is define the struct within an interface just for this purpose, and interfaces can be parameterized. So now I am defining the complex data struct here, right? And the bits per component are now a parameter of the interface. And now I can do basically exactly what I wanted. I have some other stuff in this interface, but even I could take it all out and just parameterize just this complex structure. And now I can have as, just by parameterizing this interface, I can have as much, as many different bit sizes to the complex data as I want. And of course, accessing it is just like accessing any interface. So that is the hack. And the fourth hack, and I'm going really quickly because my time is running out, is parameterized functions. Now, this is, I think, the best one, because parameterized functions cannot be parameterized directly. So this is illegal. This would be illegal in SystemVerilog, where I'd have, I find the MSB1 in a mask. This is illegal. I cannot do this function with a parameter, and then, like in this case, I would return the first one in this mask, right? I cannot parameterize a function like this and get the mask out like this. Can't do it. So in my opinion, we shouldn't have to just repeat code just to do that. And again, we can try with the packages thing, but we'll run into the same problem that we did with interfaces. So the solution is, again, use interfaces just for this purpose. For some reason, you can do it within an interface, but not the ways I suggested, which seems simpler. Anyway, put numbits mask as a parameter of the interface, then put the functions that you want inside this interface. Note that I just declared some dummy variable interface just so the compiler doesn't warn me or take error out because there's nothing in the interface. So whatever, let's keep the compiler happy, right? And now I can instantiate, my functions with the right parameters that I want instead of rewriting them all the time. And now you can see here how I do it. I just call I instantiate this mass function instant, and then I can just reference the function that I need. All right. So compiler support. These toolkits are powerful, but rely on advanced SystemVerilog support, which varies. I have tested these in Altera Quartus and Xilinx Vivado 16.1 and 2020.2 respectively and above. Other compiler support may vary, and in particular, Lattice has always given me problems, even with much simpler structures. So that, maybe it's that supported, but it's very hard to do SystemVerilog in Diamond as I don't know if you have experience with that, but that's my experience. But certainly in Vivado and Quartus, these things work. So conclusions. Efficiency is the name of the game. The more efficient you are developing code, the more you get done. There should be no need to repeat code unnecessarily by repeatedly defining and connecting pins, repeatedly needing to pass parameters down the hierarchy, repeatedly defining identical struct types, and repeatedly defining identical functions. Writing unnecessary code compounds the probability of error. Using these hacks, very big efficiency gains can be achieved and errors can be minimized. OK, that's it. Thank you.
Thank you very much, Yair. Your questions or comments?
Thank you for the nice number of hacks that you presented today. Just a question. Have you considered testing these with Synopsys like Synopsys tools or Cadence tools?
For ASICs, you mean?
Yeah. Because usually they are like a little bit more
I would love
verbose.
to. I don't have access to those tools. If someone wants to test them and tell me, I would be super happy to know. Honestly, I was really surprised that some of these hacks work, especially the one with extracting the parameters out of the interface. I was surprised. I think it didn't work for, I can't remember, I tried it for an earlier Quartus version, like I think 14, and it did not work, but 16 it started working. I'm like, well, OK, that's good.
Have you maybe tried with some open source tools like...
with what, sorry?
Some open source tools.
Oh, that may be.
Like Yosis or...
Does this support SystemVerilog? I thought it was only Verilog 2001.
I do not know, sadly.
I hope it's SystemVerilog.
So if you use the Yosis Slang plugin, the Slang front end supports it. So
I'm sorry?
Try with the Yosis Slang plugin.
Yosis what?
Not the Slang plugin. There is a SystemVerilog
open source great.
front end. It's called Slang. And we have a plugin that links it to Yosis the same way that GHDL is used with Yosis as well.
Oh, fantastic.
So try with that one. I think it has very good support.
Yeah, I would love to. Yeah, I'd love to move. I always want to move more open source. Yeah.
Hello, Martin from Silicon. Yeah, one of the things that is preventing us from using nice stuff like this is we have a code base that is heavily fragmented between VHDL and SystemVerilog, and we mix and match all the components, so we can't use all these packages and interfaces and stuff like that. Do you know anything about, is there any future in interoperability between the languages that can help people that has a lot of old IP in different languages?
I mean, we use VHDL as well. Obviously, when I have to interface VHDL to this, I unfortunately have to break out the, yes. I can't use by the interface, I have to break out the pins. Yes, I personally prefer SystemVerilog, but there's so many modules out there for VHDL that you can't avoid integrating them, right? I don't have a solution except except what you do. Yeah.
Okay, thank you.
Yeah.
Good, thank you so much. Let's thank Yair once.
Thank you. Thank you. Thank you so much.